So today we are going to take a look at Chapter 10, Liquids and Solids. And the first section is intermolecular forces. And everyone has seen this before. This is very important. Molecular means forces between molecules, not within a molecule, but between molecules. An intramolecular force would be a covalent bond. Inter would be between, forces between molecules. And the first one we're going to look at is London dispersion forces. These are also called van der Waals forces, and sometimes we just call them dispersion forces. Okay, bunch of things you need to know about London dispersion forces. These occur in all molecules. Don't forget though, molecules are only things that contain nonmetals only. And these are the only intermolecular forces for nonpolar molecules. They're caused by temporary dipoles inducing dipoles on neighboring molecules. And very important if you are comparing forces for two different molecules that are both nonpolar, you have to check your electrons. More electrons leads to more easily induced dipole, which is leading to a stronger dispersion force. Now here is a model of dispersion forces. So we've got helium over here on the left, and helium has 2 protons in the middle here and 2 electrons. Now randomly the 2 electrons might go off to the left side over here. Normally we have just a random distribution, but sometimes we get this uneven distribution of the electrons. So the electrons go to the left side. That creates some negative charge on the left side, and we still have our positive nucleus in the middle, so we end up having a slightly positive charge over on the right side because the electrons are not there. This will induce a dipole on a neighboring helium atom. So this right here on the left is this atom right here, which has the instantaneous dipole, which induces a dipole on a neighboring helium. And I'm going to show you a quick video of induced dipoles. Okay, so here we're going to look at a model of what London dispersion forces are. Here we have a bunch of any kind of atom. This could be neon or helium. Could be a molecule. It just has to be nonpolar. So here we're going to see the random electron distribution, so the electrons are evenly distributed around this atom. And then we get suddenly more electrons are on the bottom than the top. So we get a slight negative charge down here and a slight positive charge up here. Now we're going to look at the effect on the nearest neighbors. So this instantaneous dipole induces dipoles on all of its neighbors, which induce dipoles on their neighbors. So because there was this positive area up here, the negative electrons from this molecule are attracted toward the positive on this molecule, and that creates a positive up here, negative down here, and we see the effect on the neighbors. Now we're going to see instantaneous, random, suddenly, whoop, there we go. Sudden dipole right here, and they go away. Temporary induced dipole, and they go away. And that is London dispersion forces. Now we should be grateful that these London dispersion forces exist, because if they didn't, there would be no such thing as certain liquids. Nonpolar molecules could not become liquids, because there would be nothing to cause those molecules or atoms that are nonpolar to come together and form a liquid. Right. The next interaction we're going to look at is dipole-dipole interactions, or dipole-dipole attraction. This occurs between polar molecules, and the molecular dipoles line up with one another. The positive end of a molecule interacts with the negative end of another molecule. So now we're going to look at a picture of this. So here's a picture of what dipole-dipole interactions look like. On the left side over here, I've got HI molecules, oops, that are all lined up. And over on the right side, I'm just showing you where the H and where the I are on each molecule. And I'm also showing you where the interaction occurs. So the interaction is actually between the molecules. These little red dots would show you those dipole-dipole interactions. Well, that's odd. They put a They put a positive to a positive over here. This one is reversed. This should be a negative, and this should be a positive. I got this online, and I did not even notice that. So over here, I just rotated around the HI that was right over on the right here, that one, because it was reversed as well. So the I's will line up next to the H's. That's what it's telling you here. The H of one hydroiodic acid molecule interacts with the iodine of another hydroiodic acid molecule. Okay. And you all said that you like having these funny little things, so guess who this is? She's going to just say hi.
Hi.
Can you figure out who that is? I'm not going to tell you. You can try to guess in class. Okay. So the next intermolecular force we'll look at is hydrogen bonding. And this occurs between, really important, between molecules that have hydrogen bonded to N, O, or F. This is not a force within a molecule, it's a force between molecules. Oh, I didn't finish that up. So it occurs between molecules that have hydrogen bonded to NO or F, and the NO or F lone pairs on a separate molecule. So here's a picture. There's some pictures below we're going to look at also. We have a bunch of water molecules. Here's a water molecule, a water molecule, water molecule. There's a whole bunch of water molecules. And here we see little dots. Those dots are representing the hydrogen bonding. It's not an actual bond. It's an interaction between two separate molecules. It's between the H of one atom and the lone pair of an oxygen on another atom. So we have a lone pair over here on this oxygen. This is not lined up very well. So the interaction is between the H of one atom and the lone pair on another molecule. It's on the lone pair of the oxygen on another molecule. Okay, so here's some more pictures. This one shows you the difference between a covalent bond and a hydrogen bond. So right here we have our hydrogen bonding. It's not an actual bond again. And the hydrogen bonding occurs between the hydrogen of one molecule and the lone pair of another molecule. Okay, I'm going to let you look at that for a second so you can see we've got our lone pairs. These are our lone pairs here. We've got our hydrogen atoms up here. And we have our covalent bonds. Here's a covalent bond, here's a covalent bond. Here's a covalent bond, here's a covalent bond. Okay, one more picture to look at. This one is showing you that hydrogen bonding doesn't have to occur only between two molecules that are exactly the same. They can occur between two molecules that are different kinds of molecules. So here we have a water molecule and an ammonia molecule. And we still have bonding, that's hydrogen bonding, between the hydrogen of the water molecule and a lone pair that's on the nitrogen molecule. Well, the lone pair would be this big thing over here. So you can have hydrogen bonding between different types of molecules. Okay, so we're going to summarize the different intermolecular forces. All molecules have dispersion forces, the London dispersion forces, and those are the weakest of the intermolecular forces. Only polar molecules have dipole-dipole interactions, and these are the medium strength. They're the middle strength of force. The strongest forces are hydrogen bonding. And only molecules with hydrogen bonded to N, O, or F have hydrogen bonding. These are the strongest intermolecular forces. So how do we use this information? Well, we use it to explain melting and boiling points for different molecules. So let's do a problem. We're going to rank the following from highest to lowest melting temperature, which we write as T sub m. Neon, helium, water, sulfur dioxide, and chlorine. So here's our approach. First thing you should note, these are all nonmetals, so we're dealing with intermolecular forces. Later we'll talk about metallic forces and ionic bonding and melting points for metals and ionic compounds. But for now, we're just looking at all nonmetals. These are not network covalent solids, which we'll also learn about later. We're going to break these down into polar, nonpolar, and hydrogen bonding forces. Oh, I got a bug on here. Okay, so you should note, just looking at these, that H2O has hydrogen bonding. And it's the only compound or atom up there that would have hydrogen bonding. You just see it, you know it automatically. H with NO or F, hydrogen bonding. The nonpolar substances would be neon, helium, and chlorine. Neon and helium, you have single atoms. Of course, it's nonpolar. Chlorine, it's chlorine bonded to chlorine. So the difference in electronegativity is 0. So therefore, the whole thing has to be nonpolar because you don't even have a bond dipole. SO2 we need to check. The bonds will be polar. So we have to draw our Lewis structure. You have to figure out what your geometry is, add up the bond dipoles, and lo and behold, this thing is in fact polar. So we've broken everything down into substances that have hydrogen bonding, substances that are polar, and substances that are nonpolar. Now, of all those nonpolar substances, we need to check the electrons. We had that little starred note. In order to compare nonpolar substances, you have to compare the number of electrons. Now, this is not the outer electrons. This is total. I've had students over the years get confused, and they just look at the valence electrons here because you're so used to looking at valence electrons. No, 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 no. We look at total electrons. Neon has 8 electrons. Helium has 2. Chlorine, each chlorine has 17 electrons, so Cl2 has 34 electrons. Therefore, chlorine has the strongest dispersion forces, and helium has the weakest dispersion forces. So, what does this tell us? The highest melting temperature would be the substance that has the strongest intermolecular forces, and that would be water. Then we would have the next strongest forces, which would be our dipole-dipole bonds, which occur between polar molecules. So sulfur dioxide is next. And then we have our nonpolar substances, which only have dispersion forces. Chlorine has the strongest dispersion forces, so of the nonpolar substances, it would have the highest melting point, followed by neon and then helium. That's it for intermolecular forces.